So, I'm going to remedy the issue of not having a correct intro video for this lab. Right, so it's the linear acceleration we see in the title, and let's change the color. So what's our objective? So we've already learned about ticker tape, we learned how to use the spark timer, and we learned how to measure it and extract linear motion. So basically we want one objective today is to measure the acceleration of gravity. And I suppose we could add using an air track. An air track and a spark timer. Okay, so let's do some background. And let's see what kind of built-in shapes this thing has for us. Shapes. Gotta have it right triangle, no? Basic shape, there we go. Alright, so we got us a right triangle. And so we wanna have no fill. Yeah, better no fill. Okay, so let's have us, let's see if we're on a roll here. So this is going to be sort of what we're going to be dealing with. And so a block on this ramp, we know that if we have something on a ramp, it could start sliding down, and we probably have in the back of our minds that it's going to do that because of the force of gravity. And we would be right. And so we would have a vector, and let's say it comes from the center there. I guess what we have to do is we have to get rid of no fill in that shape also. There we go. And we have ourselves an angle here. And so what we can do is we can break up the weight into two components. So there's a component going down, and excuse me. Let's see, and then let's add some, make it heavier. Excuse me. And there is another component that is pointed perpendicular to the motion, and shape format, let's pick another color, and let's make it heavier. Okay, so we have this is a vector, so we call this weight parallel, and we call this weight perpendicular. And it's one of those things where these three guys CV, it turns out that, let's see, and this one is too big. That by definition, these two are at right angles to each other because they're parallel and perpendicular to that surface. And maybe you remember some trigonometry. All right. Oops. Will allow us to rotate it, huh? Control C, Control X. And then what I'll do is I'll bring it back as a picture. And then as a picture, I can rotate it, but of course it's facing the wrong way. And you see that they construct into, excuse me, oh, maybe I can I mirror this? Let's see. Look at that, huh? So this is the angle in there, theta, and so we have this trig function, hypotenuse, that says that the sine of theta equals opposite over hypotenuse. Okay, so we need the trig function because what happens is that sine of theta equals 0 if theta equals 0, and sine of theta equals 1 if theta equals 90. So if we were to take this slope and bring it all the way down to 0, then we know there'd be no force trying to push the block down the hill. And in the opposite sense, that if we raised up this ramp all the way to vertical to 90, then all the weight and the horizontal component and parallel component would both be pointed down, straight down, and that would be the maximum value. So that's why we use sine, because when the thing is flat, the ramp is flat, there's no force pushing the block, and when it's vertical, tipped all the way up to vertical, it's maximum. Because of course, remember that the weight vector always points down. Okay. So the lab manual shows that we're going to call this dimension, the hypotenuse, we're going to call it L. We're going to call this little h. So then that means that sine of theta equals opposite over hypotenuse, and the last little bit is then that weight parallel equals the magnitude of the weight vector times sine of theta, but then we can just substitute this in. So W parallel equals the weight times h over L. Pretty nifty, huh? Okay. And I think I've got it all there. All right. So, So weight is also defined as the mass times g, which is the acceleration of gravity, and we assume, well, we know that g is constant let's see, from 0 to 1,000 kilometers above the ground. Okay, so notice now, then, since mass is what we call a scalar, just a number, and it's always positive, that the weight vector and the acceleration vector always point in exactly the same direction. So that allows us then to say that the acceleration parallel is equal to the acceleration of gravity times h over L. And so we are going to measure a parallel, also called a ramp. It could be in the lab, in the manual to write up. Let's see. Not sure. Okay, what's next? So then at the end of the day, we can have a measured acceleration of gravity, which, g, and which should be an acceleration of gravity there, or g. So notice that acceleration of gravity is equivalent to saying g. We just have to solve for it, equals, so that's the measure up, equals the A parallel measured times now L over H. Okay, so that's our background. Let's call this equation 1, equation 2. So now, well, let's see. Let's just call that the background.